All right, so nonpolar, larger the atom, more electrons is going to mean that it has more possibility for more possibility for polarizability. All right. So then what if you're comparing two things and you don't know which one is greater? Now, if two molecules are comparable size and shape, dipole-dipole interactions are greater than London dispersion. If one molecule is much larger than the other, then dispersion forces will likely determine its physical properties. In other words, if you have this humongous compound, right, you have like 20 carbons and a whole bunch of hydrogens and all that stuff, then London dispersion is probably going to be greater than a dipole if you're comparing it to, water or something. Okay? All right. So when you look at the comparison in terms of, if I'm comparing hydrogen sulfide to selenium to tellurium, and you're looking at obviously the periodic table and you see them, and it makes sense, sulfur is less than selenium and so on. The temperature increases as we're moving. But water really doesn't follow any trend. Okay, and that's because of that H bonding. So water should be down here in all reality, but it happens to be up here because of the H bonding. Okay, so keep that in mind, that water doesn't follow the normal trend. So now hydrogen bond is between an electronegative element bonded to hydrogen like nitrogen or oxygen, and that attraction to, again, another electronegative element. So you have a partial positive and a partial negative. Hydrogen is always going to get the partial positive. So usually you find the H bonding when hydrogen is bonded to nitrogen, oxygen, or fluorine, because those are your most electronegative elements that it's going to bond to. And that's going to cause the hydrogen to have that pull of the exposed nucleus of the hydrogen, because the electrons are being pulled by the electronegative element that it is bonded to. Yes?
Sorry, will you go back a slide?
Sure. This one?
Yeah.
So hydrogen bond is really a dipole-dipole, but it's specifically to hydrogen. It's the same kind of concept, except it's stronger than just a regular dipole-dipole. Okay?
Is it just nitrogen, oxygen, and fluorine?
Fluorine, yeah. That's usually where you have the most polar bonds with hydrogen. Okay? All right. So, intermolecular forces, you have 4 kinds. So London dispersion induced, dipole-dipole, hydrogen bonding, and ion dipole. So what you're looking for is if there are ions involved, then it's either ion, it can be ion dipole, right? Where you don't have any ions involved, then you look to see, is it polar? If it's not polar, then you're dealing with London dispersion. If it is polar, does it have a hydrogen bonded to nitrogen, oxygen, or fluorine? Then you're dealing with hydrogen bonding. Otherwise, it's just dipole-dipole. Okay? All right, I'm going to give you a 3-minute break because you guys look like you're about to sleep. So, all right, let's take 3 minutes, go use